On the morning of February 9, 1943, Lieutenant Philip DeLong nursed his crippled F4U Corsair across the Solomon Sea, smoke trailing from the engine cowling like a funeral shroud. The combat patrol had started routinely enough. Sweep the skies above Bougainville, protect the bombers, return to base. But a swarm of Zeros had descended from the cloud cover, and during the violent engagement that followed, enemy fire had chewed through his oil lines. Now, with the engine temperature gauge climbing into the red and the stick growing sluggish in his hands, DeLong faced the ancient aviator's dilemma: bail out over water and hope for rescue, or try for a controlled landing somewhere, anywhere, on enemy-held territory. The decision was made for him when the engine seized with a grinding shudder that shook the entire airframe. Below, the green canopy of the jungle stretched endlessly, but DeLong spotted a clearing near what looked like a coastal plantation. He brought the Corsair down hard, the landing gear crumpling as the aircraft plowed through soft earth and vegetation. The impact threw him against his harness, and when the world stopped spinning, he found himself sitting in a remarkably intact fighter, surrounded by the eerie silence of the jungle. Within hours, Japanese infantry patrols converged on the crash site. DeLong had already disappeared into the thick undergrowth, beginning a desperate trek that would eventually lead to his rescue by Australian coast watchers 3 weeks later. But he left behind something far more valuable than he could have imagined: an almost undamaged example of America's newest carrier fighter, complete with its revolutionary inverted gull wing, its massive Pratt & Whitney R2800 engine, and most critically, its advanced gunsight and radio equipment. Captain Yoshiro Hashiguchi of the Imperial Japanese Navy's Technical Intelligence Unit arrived at the site 2 days after the crash. A graduate of Tokyo Imperial University's engineering program, Hashiguchi had spent the pre-war years studying American aviation journals and had even toured several American aircraft factories in 1938 as part of a diplomatic mission. He considered himself knowledgeable about American aircraft design philosophy. But when he first laid eyes on the Corsair, still sitting in the clearing where DeLong had left it, Hashiguchi felt something he rarely experienced: genuine intimidation. The aircraft was enormous compared to the lightweight Zero fighters he was accustomed to analyzing. Its bent wing configuration was unlike anything in the Japanese inventory, and when his team began their initial measurements, the numbers seemed almost fantastical. The propeller alone was over 13 feet in diameter. The engine displacement dwarfed anything Japan had managed to produce. Most troubling of all was the aircraft's construction: heavy-gauge aluminum, robust fastening systems, and a build quality that spoke of massive industrial capacity. According to declassified records from the United States Naval Institute archives, this particular Corsair, Bureau number 02155, would become one of the most thoroughly studied American aircraft to fall into Japanese hands during the entire Pacific War. Hashiguchi immediately ordered the aircraft secured and arranged for its transport to Rabaul's main technical facility, where his team of 30 engineers and technicians waited. The process would take nearly 3 weeks, requiring the Corsair to be partially disassembled and carried through the jungle on improvised sleds pulled by impressed laborers. But Hashiguchi knew the intelligence value justified any effort. The Americans had brought something new to the Pacific theater, and understanding it might mean the difference between victory and defeat in the skies overhead. On March 2, 1943, the captured Corsair finally arrived at the Japanese naval facility in Rabaul, New Britain. Lieutenant Commander Jiro Horikoshi, designer of the legendary Zero fighter, had traveled from Japan specifically to examine this prize. As the aircraft was carefully unloaded from the transport trucks, Horikoshi walked slowly around it, his experienced eye cataloging every detail. He had heard reports of the American bent-wing fighter from combat pilots, but seeing it firsthand was an altogether different experience. The engineering team worked through the night, setting up floodlights around the Corsair and beginning their systematic analysis. Chief Engineer Saburo Takada directed the initial documentation phase, with photographers capturing every angle, every panel line, every visible component. The team's preliminary report, completed within 48 hours, read like a letter of grudging admiration from one engineer to another across enemy lines. The inverted gull-wing design immediately captured everyone's attention. Horikoshi spent hours examining the wing root joints, the complex angles where the wing met the fuselage. The bend served multiple purposes, his team concluded. It allowed for shorter, stronger landing gear while maintaining adequate propeller ground clearance. It positioned the wing's center section at the ideal angle for maximum lift, and it actually reduced overall drag by allowing the wing to meet the fuselage at a near perpendicular angle. It was elegant problem-solving, the kind that made Horikoshi both envious and respectful of his American counterparts. Takada's team focused on the power plant. The Pratt & Whitney R2800 double wasp engine represented a quantum leap in aviation technology. With 18 cylinders arranged in 2 rows, it produced over 2,000 horsepower, nearly double what Japan's most powerful engines could deliver. When they pulled the engine cowlings and examined the supercharger system, the Japanese engineers found themselves confronting uncomfortable truths about the industrial gap between their nations. The precision machining, the quality of metallurgy, the sophistication of the cooling systems, all of it pointed to manufacturing capabilities that Japan simply could not match in 1943. The bearing tolerances alone are beyond our current production capacity, Takada wrote in his report to Naval Headquarters in Tokyo. The Americans are not simply ahead in design. They possess fundamental industrial advantages that cannot be overcome through engineering cleverness alone. This assessment, preserved in captured Japanese documents now held by the National Archives in College Park, Maryland, represented a rare moment of brutal honesty in wartime reporting. The armament impressed and worried the Japanese analysts in equal measure. 6 Browning M250 caliber machine guns, 3 in each wing, with over 400 rounds per gun. The firepower concentration was devastating. Japanese fighters typically carried 2 20mm cannons and 2 7.7mm machine guns. The Corsair's 6 heavy machine guns could put more metal into the air per second than an entire 3-plane Zero formation. But it was the gun sight that truly fascinated them. The Mark 8 reflector sight was a technological leap beyond anything in Japanese fighters. Takada carefully disassembled it, documenting the optical system, the illumination mechanism, the lead computing features. Here was a device that took much of the guesswork out of aerial gunnery, allowing even relatively inexperienced pilots to achieve hits that would have required exceptional skill in a Zero. The radio equipment presented another revelation. American pilots could communicate clearly over dozens of miles, coordinating their attacks with a precision that Japanese formations could never match. The Japanese Navy's radios were notoriously unreliable, often forcing pilots to rely on hand signals and wing-waggling for basic communication. The Corsair's radio, by contrast, was compact, powerful, and apparently robust enough to survive the rigors of carrier operations. By mid-March of 1943, Horikoshi's team had completed their initial assessment and begun writing detailed technical reports for distribution to Japanese aircraft manufacturers. But the process of analyzing the Corsair had evolved beyond simple intelligence gathering. It had become an uncomfortable confrontation with industrial reality. On March 18th, Horikoshi sent a confidential memo to Admiral Isoroku Yamamoto that was remarkable for its candor. "We are not facing a superior design," Horikoshi wrote. "We are facing a superior industrial system. The Corsair represents not innovation but capacity. The capacity to build heavy fighters with powerful engines, to equip them lavishly with radios and ammunition, to manufacture precision components in quantities we cannot match. The Zero succeeds through lightness and agility. The Corsair succeeds through the application of overwhelming resources." Takada's metallurgy team had begun conducting destructive testing on various Corsair components, cutting through aluminum sections to analyze the alloy composition and examining stress points for manufacturing techniques. What they discovered was a consistent story of industrial abundance. The Americans used thicker aluminum than strictly necessary, creating built-in safety margins that Japanese designers, working with limited materials, could never afford. The fasteners were larger and more numerous than Japanese practice would dictate. The hydraulic lines were reinforced beyond minimum requirements. "They build as if they have infinite aluminum," noted engineer Kenji Yoshida in his materials assessment report. "We build as if every gram of metal might be the difference between producing one more fighter or none at all." The armor plating particularly impressed the Japanese analysts. The Corsair featured substantial armor protection for the pilot. thick plates behind the seat, armored glass in the windscreen. Japanese fighters carried minimal armor, sacrificing protection for weight savings and maneuverability. The Zero could outturn the Corsair, but a single hit from heavy-caliber fire could prove catastrophic. The Corsair could absorb punishment that would destroy a Zero and still bring its pilot home. The team attempted to run the Corsair's engine, hoping to conduct performance tests. They spent days repairing the damage DeLong's forced landing had inflicted, replacing oil lines and checking for internal damage. On March 23rd, they finally achieved startup, and the massive double Wasp engine roared to life with a deep, thunderous sound utterly unlike the high-pitched scream of Japanese radial engines. They ran it for 17 minutes before a coolant leak forced them to shut down. But those 17 minutes provided invaluable data. According to records preserved in the Naval Aviation Museum in Pensacola, Florida, Japanese intelligence reports from this period show a significant shift in tactical recommendations. Where earlier assessments had focused on exploiting the Zero's superior maneuverability, reports after the Corsair analysis emphasized avoiding engagement when possible and recommended developing new tactics specifically to counter the American fighter's advantages in speed, firepower, and diving performance. Horikoshi proposed several modifications to Japanese fighter designs based on lessons from the Corsair. He advocated for stronger airframes that could handle higher speeds, improved radio equipment, and more powerful engines. But when his proposals reached the manufacturing sector, they encountered harsh reality. Japan's aluminum production was already stretched thin. The precision bearings required for more powerful engines were in critically short supply, needed equally for tanks, ships, and aircraft. The optical glass for improved gun sights was simply unavailable in the quantities required. "We understand what needs to be done," Horikoshi confided to a colleague, in a conversation later recorded in the post-war memoir of engineer Masatoshi Okumiya. "We lack only the means to do it." The psychological impact of the Corsair analysis rippled through Japan's aviation establishment. Senior engineers who had spent their careers developing lightweight, maneuverable fighters now confronted a different philosophy: the American approach of using massive engines to compensate for weight, of accepting reduced agility in exchange for speed and firepower, of building aircraft that prioritized pilot survival alongside combat effectiveness. By early April of 1943, the technical analysis of the captured Corsair had expanded to include combat pilots who had faced the type in battle. The Imperial Japanese Navy gathered its most experienced aviators at Rabaul for detailed debriefing sessions, using the captured aircraft as a visual reference. What emerged from these discussions was a tactical picture that disturbed even the most confident pilots. Lieutenant Saburo Sakai, one of Japan's leading aces with over 60 confirmed victories, examined the Corsair with the practiced eye of a combat veteran. He climbed into the cockpit, noting the excellent visibility provided by the raised seat position and the bubble canopy. The Americans had solved problems that Japanese designers seemed to ignore. The Zero's cockpit visibility was good forward but limited to the sides and especially to the rear. The Corsair pilot sat high, with clear sightlines in nearly every direction. "In the Zero, we rely on wing mirrors and constant head movement to maintain awareness," Sakai explained to the assembled engineers. "The American pilot sits in a greenhouse. He can see threats developing before they become critical. This is worth perhaps 2 seconds of reaction time. In combat, 2 seconds is an eternity." The control layout impressed the Japanese pilots. Everything seemed designed around the principle that a pilot under stress, exhausted and possibly wounded, should be able to operate his aircraft with minimum confusion. Controls were logically grouped, clearly labeled, and positioned within easy reach. Japanese fighters, by contrast, often featured controls scattered around the cockpit based on engineering convenience rather than pilot ergonomics. Captain Minoru Genda, one of the architects of the Pearl Harbor attack and now serving as an air operations analyst, pushed the discussion beyond individual aircraft capabilities to broader strategic implications. On April 7th, he delivered a presentation to senior staff that used the Corsair as a symbol of American military-industrial power. "This aircraft represents their opening move in the second phase of this war," Genda argued. "The Zero gave us air superiority in 1941 and 42. The Americans have now studied our tactics, analyzed our aircraft, and developed specific counters. The Corsair is not trying to outturn us. It is designed to leverage American advantages while negating ours. They will dive on us from superior altitude, using their speed advantage. They will extend away when we try to engage, refusing to fight on our terms. They will use their superior radios to coordinate attacks that overwhelm our formations through numerical concentration. The technical team had by now measured every significant dimension of the Corsair and calculated its performance envelope. The numbers were sobering. Maximum speed exceeded 400 miles per hour at altitude, roughly 50 miles per hour faster than the latest Zero variants. Rate of climb was exceptional, thanks to that massive engine. Diving speed was limited only by pilot endurance and structural strength, both of which exceeded Japanese standards. The only performance category where the Zero maintained clear superiority was turning radius and sustained turn rate. "They have created an aircraft that refuses to fight our fight," observed Commander Masatake Okumiya during a tactical symposium recorded in post-war interviews for the United States Strategic Bombing Survey. In 1941, we dictated the terms of engagement. Now the Americans have that option. Their pilots can choose to engage when advantageous and decline when not. We cannot force them to fight in the slow-speed, turning battles where the Zero excels. The maintenance and logistics aspects of the Corsair also revealed American operational philosophy. The aircraft was designed for rough handling by carrier deck crews. Panels were large and easily removed. Major components could be replaced in the field without elaborate tools or facilities. The Japanese observed that American aircraft design seemed to assume that mechanics would sometimes be semi-trained personnel working in adverse conditions. Japanese fighters, by contrast, required careful handling by experienced technicians. This observation pointed to another uncomfortable truth. The Americans were preparing for a long war and designing their equipment accordingly. They expected to train thousands of new pilots and tens of thousands of new mechanics. They were building aircraft that could be maintained by these relatively inexperienced personnel. Japan's approach assumed a smaller force of elite pilots and highly skilled ground crews, an approach that worked brilliantly in the war's opening phase but became increasingly untenable as casualties mounted. On May 3, 1943, Horikoshi completed his comprehensive report on the captured Corsair and its implications for Japanese naval aviation. The document, running to over 200 pages with detailed technical drawings and performance analyses, circulated among the highest levels of military command. Its conclusions were stark enough that several officers initially questioned whether the report should be distributed more widely, fearing its impact on morale. The report's executive summary pulled no punches. The F4U Corsair represents a fundamental shift in American fighter design philosophy and, more significantly, demonstrates industrial capabilities that Imperial Japan cannot currently match. While we can understand the engineering principles behind this aircraft, we lack the manufacturing infrastructure and raw materials to produce comparable machines in militarily significant numbers. Furthermore, the Corsair is almost certainly not an isolated development. If American industry can produce aircraft of this caliber, we must assume they have other advanced designs in development or entering service. Admiral Yamamoto read Horikoshi's report during a series of inspection tours through the South Pacific. According to his Chief of Staff's diary, later examined by historians researching materials at Japan's National Institute for Defense Studies, the Admiral's response was characteristic. "We have awakened a sleeping giant and filled him with terrible resolve. Now we see what that giant can build when fully roused. The question is not whether we can match these machines individually. We cannot. The question is whether we can develop tactics and strategies that allow our warriors' spirit to overcome material disadvantage." But spirit, however fierce, could not change physics or overcome industrial disparities. The technical team at Rabaul had calculated that the Corsair's fuel capacity gave it significantly longer range than many Japanese observers had assumed. This meant American fighters could escort bombers deeper into Japanese-held territory, protecting them throughout their missions rather than only at the periphery of their range. It meant American carriers could launch strikes from greater distances, complicating Japanese efforts to locate and attack the carrier task forces. The armor and structural strength findings had equally troubling implications. Japanese pilots were reporting that their 20mm cannon shells often seemed to have reduced effectiveness against American fighters. The captured Corsair explained why. Its robust construction meant that shells might punch through the aircraft without encountering critical components. The redundant systems, dual hydraulic lines, backup controls, protected fuel tanks, meant that damage that would down a Zero might only degrade a Corsair's performance slightly. Engineer Takata had documented the Corsair's self-sealing fuel tanks in excruciating detail. These tanks, lined with layers of rubber and other materials, could automatically seal small punctures caused by bullets or shell fragments. Japanese fighters lacked this technology. A single incendiary round in a fuel tank could transform a Zero into a fireball within seconds. The Corsair could take multiple hits to its fuel system and remain flyable. By late May, the captured Corsair had been disassembled into major components for shipment to Japan, where it would undergo even more detailed analysis at the Yokosuka Naval Arsenal. But before the aircraft left Rabaul, the technical team conducted one final test that would become legendary in Japanese aviation circles. They attempted to replicate typical American tactical maneuvers with Japanese pilots flying the Corsair against Zero fighters. The results were humbling. Even though the Japanese test pilots had only minimal familiarization with the Corsair's controls and characteristics, they found they could largely dictate the terms of engagement. When they maintained their energy advantage, staying fast and using diving attacks, the Zeros struggled to counter them effectively. Only when the Corsair pilot made mistakes, bleeding off speed and turning fights, or allowing Zeros to climb to comparable altitudes, did Japanese tactics become effective. The aircraft teaches as it fights, noted Lieutenant Commander Takeo Shibata, one of the test pilots, in his after-action report. The American pilot who follows his training and uses his aircraft's strengths properly is nearly untouchable by our current tactics. Only inexperience or overconfidence makes him vulnerable. As American pilot training improves, our window of opportunity narrows. These conclusions reached Tokyo at a critical moment. Japan's strategic position in the Pacific was deteriorating. The Americans had secured Guadalcanal after months of brutal fighting. Their submarine campaign was beginning to strangle Japanese supply lines, and now intelligence reports indicated that the Corsair was just one of several new American aircraft types entering service: the P-38 Lightning, the P-47 Thunderbolt, the F-6F Hellcat. All of them were big, powerful, heavily armed fighters designed around the same philosophy as the Corsair. Throughout June and July of 1943, Japanese Naval Aviation Command struggled to formulate an effective response to the Corsair and similar American fighters. The captured aircraft had provided superb intelligence about American capabilities, but intelligence alone could not bridge the gap between understanding a problem and solving it. 3 separate initiatives launched during this period illustrated both the creativity of Japanese engineers and the fundamental limitations they faced. The first initiative focused on tactical adaptation. On June 15th, the Imperial Japanese Navy issued revised combat doctrine specifically addressing engagements with heavily armed American fighters. Pilots were instructed to avoid head-on attacks, where the Corsair's .650 caliber machine guns gave it overwhelming firepower advantage. They were directed to use teamwork to force American fighters into slow-speed maneuvering fights where the Zero's advantages could be exploited. Most critically, they were ordered to maintain altitude whenever possible, negating the American tactic of diving from superior height to attack and then extending away before Japanese fighters could respond. But tactical doctrine could only achieve so much when the underlying hardware disparities remained. American pilots flying Corsairs could simply refuse engagements when conditions were unfavorable. Japanese pilots, often committed to protecting bombers or defending specific locations, lacked that luxury. They had to fight when and where American commanders chose to engage. The second initiative involved attempting to incorporate lessons from the Corsair into Japanese fighter development. Horikoshi and his team proposed several modifications to the next generation of Japanese naval fighters. They recommended more powerful engines, heavier armament, improved armor protection, and stronger airframes capable of higher diving speeds. The resulting design proposals, particularly the A7M Reppu, incorporated many insights gleaned from studying the captured Corsair. However, the development timeline told a story of industrial limitation. The A7M would not fly until October of 1944, and production difficulties meant only a handful would be completed before war's end. According to post-war analyses conducted by the United States Naval Technical Mission to Japan, the delays stemmed largely from Japan's inability to manufacture critical components in sufficient quantities. The powerful engines required bearings that Japan's industry struggled to produce. The heavier airframe needed aluminum alloys that were increasingly scarce. Even seemingly simple components like reliable radios required materials and precision manufacturing that was stretched thin across Japan's entire war effort. The third initiative, perhaps the most ambitious, involved attempting to directly copy certain Corsair technologies. In August of 1943, a team at the Nakajima Aircraft Company received detailed drawings and specifications for the Corsair's propeller, engine mounting system, and gun sight, along with the actual components from the captured aircraft. Their assignment was to reverse engineer these items and develop Japanese versions that could be adapted to existing fighter designs. Engineer Takashi Yamamoto led the propeller project. The Corsair's three-bladed Hamilton Standard propeller was a masterpiece of precision engineering. Each blade was carefully shaped to optimize thrust across a wide range of speeds and altitudes. The hub mechanism that allowed the blades to change pitch was robust, yet sophisticated. Yamamoto's team spent months measuring, analyzing, and attempting to recreate the propeller. They succeeded in building prototypes that looked similar to the original, but performance testing revealed persistent problems. "We can copy the shape, but we cannot reproduce the material properties," Yamamoto reported to his superiors in a memo preserved in Nakajima's wartime records, now held at the National Archives of Japan. "The American aluminum alloys possess strength and fatigue resistance superior to our current materials. Our propellers work, but they are heavier and less reliable than the original. Under combat stress, they fail sooner." The gunsight project encountered different obstacles. Japanese optical industry had always struggled with the precision glass required for high-quality sights. The Corsair's reflector sight used optical elements ground to tolerances that Japanese manufacturers could achieve only in small batches with high reject rates. Producing such sights in quantities sufficient for frontline fighters would have required diverting optical manufacturing capacity from other critical needs: periscopes for submarines, rangefinders for warships, optical equipment for artillery. By September of 1943, it had become clear that Japan's attempts to quickly close the technological gap were failing. The captured Corsair had provided a perfect blueprint of what needed to be built, but a blueprint was useless without the industrial capacity to execute it. As 1943 progressed into its final months, the captured Corsair in Yokosuka became almost a shrine of sorts, a place where Japanese engineers and pilots came to see firsthand what they were up against. By October, American Corsairs were operating in increasing numbers throughout the Pacific theater. The intelligence that had seemed so valuable in February now felt almost like a cruel joke. The Japanese knew exactly what they faced and understood precisely why they were overmatched, yet possessed no means to correct the imbalance. Lieutenant Commander Horikoshi made several trips to Yokosuka that autumn to examine the Corsair and confer with colleagues about Japanese aviation's future. During one visit in early November, he spent an afternoon simply sitting in the captured fighter's cockpit, contemplating the profound differences between American and Japanese approaches to warfighting. Later, he wrote in his personal journal, portions of which were published decades after the war, about the psychological impact of the Corsair analysis. "We Japanese engineers pride ourselves on innovation, on doing more with less, on the elegance of our solutions to complex problems," Horikoshi wrote. The Zero embodied this philosophy, a fighter of exceptional performance built with minimal materials. But the Americans have shown us a different path. They do not seek elegance in scarcity. They achieve superiority through abundance. The Corsair is not an elegant solution to limited resources. It is an overwhelming application of unlimited resources. And against such an approach, all our cleverness may not be enough. The combat reports flowing in from the front lines confirmed Horikoshi's fears. American pilots, many of them relatively inexperienced, were achieving kill ratios that would have been impossible in the war's early years. Not because they were suddenly more skilled than their Japanese opponents, but because their aircraft forgave mistakes that would prove fatal in a Zero. An American pilot could survive errors in judgment, could absorb punishment, could rely on superior speed to escape disadvantageous situations. Japanese pilots had no such margins for error. Saburo Sakai, recovering from severe injuries sustained in combat, visited the captured Corsair during his convalescence. Walking around the aircraft, touching its heavy aluminum skin, examining its robust landing gear, Sakai experienced a revelation that he would later describe in his memoir, Samurai. He had shot down over 60 enemy aircraft during his career, but he recognized that era was ending. The quality of Japanese pilots remained high, perhaps even superior to most American aviators in terms of pure flying skill and aggressive spirit. But increasingly, that superiority was irrelevant. The Americans were fielding machines that didn't require elite pilots to be effective. I realized, looking at that bent-wing fighter, that we had already lost the war, Sakai recalled in post-war interviews preserved by the Yasukuni Museum. Not lost it in 1945 or 44, but back in 1942, perhaps even 41. We had won the opening battles with warriors and clever designs. But the Americans were preparing to win with factories and resources. The Corsair was just the first wave. Behind it would come more and more and more, in numbers we could never match. By December of 1943, American Corsairs were regularly engaging Japanese fighters over Rabaul itself, the very base where the captured aircraft had first been analyzed. The symbolism was not lost on Japanese personnel. They had dissected the Corsair, understood its secrets, and none of it had mattered. The Americans simply built more Corsairs, more Hellcats, more Lightnings, while Japanese production struggled to replace losses. The final report on the captured Corsair, completed in late December by a joint team of engineers and intelligence officers, made for grim reading. After nearly 10 months of intensive study, after thousands of man-hours of analysis, after attempting to copy or counter virtually every system on the aircraft, the conclusion was brutally simple. Japan could not build a Corsair equivalent, could not effectively counter the Corsair in the quantities now appearing, and would face increasingly dire circumstances as more advanced American aircraft entered service. The F4U Corsair program demonstrates several key principles of American military production, the report concluded, in language preserved in captured Japanese documents at the National Archives. First, their industrial capacity permits the simultaneous development of multiple advanced weapons systems. While we struggle to produce one new fighter type, they field several. Second, they design for mass production from the outset, while we design for performance and improvise production methods later. Third, they accept higher cost per unit in exchange for superior performance, while we seek minimal cost even at the expense of capability. Fourth, they design to the capabilities of average pilots and maintainers, while we design for elite personnel. These are fundamental philosophical differences that cannot be overcome through tactical adjustments or minor technical improvements. The story of the captured Corsair did not end with Japan's final technical report in December of 1943. Throughout the remaining years of the war, that single aircraft continued to serve as both reference point and reality check for Japanese aviation personnel. As the war situation deteriorated through 1944 and into 45, engineers and officers returned again and again to the lessons learned from analyzing the bent-wing fighter. In February of 1945, with American B-29s firebombing Japanese cities and the home islands preparing for invasion, Lieutenant Commander Horikoshi wrote a final assessment of the Corsair's impact on Japanese naval aviation. By this point, the captured aircraft itself had been destroyed in an American bombing raid on Yokosuka in March of 1944, but its influence persisted. The Corsair taught us what we were unwilling to see, Horikoshi wrote in this final report, later discovered among his papers by historians from the Japan Aerospace Exploration Agency. We believed our warrior spirit and technical cleverness could overcome material disadvantages. The Americans showed us that sufficient material superiority, intelligently applied, eventually defeats any amount of spirit and cleverness. This is not a pleasant lesson for proud engineers to learn, but it is an essential one. Future generations of Japanese engineers must remember, individual brilliance matters, but systemic capacity matters more. The pilots who had faced Corsairs in combat carried their own lessons forward. Those who survived the war, men like Saburo Sakai, who lived until 2001, often spoke of the Corsair with a mixture of respect and frustration. They had not been defeated by better pilots or superior tactics, but by better tools. American aviators flying Corsairs were certainly brave and often skilled, but their success stemmed as much from industrial advantage as individual prowess. After the war ended in August of 1945, American technical intelligence teams swept through Japan, examining what remained of the country's aviation industry. They discovered extensive documentation of the captured Corsair analysis, reports, photographs, technical drawings, even pieces of the aircraft that had been stored in various locations for further study. The thoroughness of Japanese engineering analysis impressed the American investigators. Japan had understood exactly what they faced. Understanding, however, had not been enough. In post-war interviews conducted by the United States Strategic Bombing Survey, Japanese engineers were remarkably candid about their wartime experiences. Engineer Takata, who had led much of the Corsair's physical analysis, explained the emotional toll of detailed knowledge without the ability to respond. Imagine knowing exactly how your opponent's sword is made, understanding every technique used in forging the blade, recognizing the superiority of the metallurgy, yet being unable to produce comparable steel, Takata told his American questioners in October of 1945. That was our position. The Corsair was an open book to us. We learned its every secret, and every secret we learned emphasized how far behind we had fallen. The captured F4U Corsair story eventually became part of the larger narrative of World War II's industrial warfare. Military historians studying the Pacific War recognized the incident as a perfect microcosm of the conflict's essential character. Japan's tactical victories in the war's opening phase had been achieved with excellent equipment, superb training, and aggressive leadership. But America's industrial mobilization produced a tidal wave of advanced weaponry that eventually overwhelmed Japanese defenses regardless of tactical skill or warrior spirit. By the 21st century, the story of Japan's captured Corsair had become a standard case study in military academies worldwide, illustrating several key principles: the importance of industrial base in modern warfare, the limitations of tactical excellence when facing systemic disadvantages, and the value of technical intelligence even when response options are limited. The original aircraft, Bureau number 02155, was never recovered. It disappeared into the rubble of wartime Japan, destroyed by the very bombing campaign that American industrial might made possible. But its legacy persisted in the detailed reports Japanese engineers produced, in the tactical adjustments those reports prompted, and ultimately in the historical memory of an empire that learned, perhaps too late, that understanding your opponent's advantages and possessing the means to counter them are two entirely different things. On the other side of the Pacific, Lieutenant Philip DeLong, the pilot who had crash-landed that Corsair in February of 1943, survived his ordeal in the jungle and the rest of the war. He never knew the full extent to which his abandoned aircraft had influenced Japanese thinking about naval aviation. He returned to civilian life, raised a family, and lived until 1997. In his later years, he occasionally spoke to aviation historians about that forced landing on Bougainville. "I was just trying to survive," DeLong recalled in an interview published in Aviation History magazine in 1994. "I never imagined those Japanese engineers would spend months analyzing that airplane, and I certainly never guessed that what they learned wouldn't matter much in the end. We just kept building more Corsairs, more Hellcats, more everything. That's what won the war. Not any one airplane or battle, but the simple fact that we could produce faster than they could destroy." And perhaps that was the ultimate lesson of the captured Corsair, that in industrial warfare between modern nations, production capacity shapes destiny more surely than any individual weapon system, no matter how thoroughly understood or brilliantly designed. The Japanese engineers who examined that bent-wing fighter in early 1943 came to understand American aircraft design at a deep, technical level. But understanding alone could not build factories, could not produce aluminum, could not train thousands of new pilots and mechanics. The Corsair was exceptional not because it was a mystery the Japanese couldn't solve, but because it was a challenge they couldn't match, and that made all the difference in the skies over the Pacific.